Hello. In this video we will touch on the concept of electrostatic force, which is the force that is exerted between electrically charged particles. All the particles we have talked about have a property called mass, which is a property that defines how much the object resists attempts to accelerate it. We also saw that mass is a crucial property in determining the strength of gravitational attraction. Similarly, all particles have a property called electric charge, or just charge. Like mass, the electric charge of one particle might be smaller than the charge of another particle. Unlike mass, however, electric charge can have both a positive or a negative value. So, for instance, one particle could have positive 1 coulomb of charge, and the other could have negative 2 coulombs of charge. A coulomb is the standard unit of charge, just as a kilogram is the standard unit of mass. A coulomb can just be written as capital C to save time and space. Also, a particle could have a charge of 0 coulombs, which we would call neutral, since it is neither positive nor negative. Two charged particles will always exert an electric force on each other, just as two particles with mass exert a gravitational force on each other. With gravity, that force is always attractive, which means that the two particles always try to get closer together. With electric force, it depends. If one particle is positive and the other is negative, they are said to have opposite charge. In that case, the charges will exert an attractive force on each other. If you've ever heard the phrase opposites attract, it's a reference to this phenomenon. If, however, both charges are negative or both charges are positive, then they are said to have like charge, and then the two particles will repel each other, which means that they will exert a force that tries to push them further apart. Now that we understand how to determine the direction of the force, let's actually learn how to compute its magnitude. This is the formula for the gravitational force as a comparison, and this is the formula for the electrostatic force. They are actually very similar. The k in the electrostatic force equation is a universal constant that has this value. It serves a similar role as the big G in the gravity formula. The Q1 and Q2 terms represent the charge of the objects. The larger the charges involved, the greater the strength of the electric force. This is just like how the larger the mass is, the greater the gravitational force. Notice that if one of the charges is neutral, which means it equals 0, then the force is 0. We also divide by r squared, where r is the distance between the two particles. So, the further apart the charged particles are, the weaker the electric force will be. Again, this is exactly like gravity. Finally, you might have noticed that there is a negative sign over here. If we just cared about the magnitude of the electrostatic force, then we could ignore the negative, and not care about the signs of the charges either. However, if we adopt the convention that a positive force is attractive and a negative force is repulsive, then this negative sign is very useful. If we include the signs of the charges when plugging values in, then we will get a positive value if the force is attractive, and we will get a negative value if it's repulsive. Let's show how this works. If both charges are positive, then Q1 times Q2 is definitely positive, but the negative sign on the outside makes the force as a whole negative. That means the force is repulsive, which makes sense because the two charges have the same sign. Similarly, if both charges are negative, then a negative times a negative is a positive, so Q1 times Q2 is positive. However, we still have the negative in front, so the force as a whole is negative, which means repulsive. Again, this works with our principle that like charges repel. Finally, if one charge is positive and the other is negative, then Q1 times Q2 will be negative. Then we multiply that negative by the negative sitting in front, and we get a positive, which means the force is attractive. This fits with our principle that opposite charges attract. Let's do a quick example with the numbers you see on the diagram. Let's plug those numbers into the force equation, making sure to include the signs on the two charges. This will get us negative k times negative 2 coulombs squared divided by 4m squared. The negative signs cancel, so we are left with k times a half, and the units are still c squared over m squared. Now we multiply the value of k in, which is 9 times 10 to the 9th, and we get 4.5 times 10 to the 9th newtons. Since the result is positive, the force is attractive. I suggest you pause here and make sure you follow how the units became a newton. Now, 10 to the 9th newtons is huge. We have never seen forces like that before. The truth is that even with electrostatic forces, you won't find this kind of force, because objects almost never have a whole coulomb of charge. Typically, charge is on the order of 10 to the minus 6 coulombs, or a millionth of a coulomb. So if our problem was actually with charges on that scale, we would find that the force is actually only 4.5 times 10 to the minus 3rd newtons, which is pretty small. In summary, objects have a property called electric charge. The electric charge can be positive, negative, or even zero. Any two charged particles exert a force on each other. If they are like charges, they repel each other, but if they are oppositely charged, they attract each other. The strength of this attraction is given by this formula. If the result of the formula is positive, then the force is attractive, but if the result is negative, then it is a repulsive force. And that's it. Thanks for watching.